Okay, so today I'm going to continue with sub-GeV dark sectors and start talking about, going into some more detail about some of the cosmology and constraints and all this model building stuff. So let's just do a quick recap of last time. I'm going to draw the three benchmarks that I introduced last time, and then one of them I didn't really get to last time, so we'll do a recap by just reviewing, going over that benchmark. So we have this direct, this is, I'm going to call it direct, but it means thermal relic. So that's where I had standard model particles directly annihilating with dark matter back and forth, and that sets the relic abundance. I had my secluded, where the relic abundance is set by annihilation to some new light mediator. And the third one was freeze in, which was the one I actually didn't really go over at all, which was only annihilation into standard model particles was in equilibrium. And so I was going to use the notation as last time that anytime I have a coupling of the mediator with dark matter, it's just called GX. And if I have a coupling with a standard model in the mediator, it's GF. Okay, so what we did last time, very briefly, we got this useful relation that if you want to get the 100% of the dark matter relic abundance today, then you should compute whatever its freeze out co-moving number density is and set it equal to an EV over mx.
Which does not apply for the category 3, I'm assuming?
I'm about to apply it to category 3. So we did it for category 1 and 2, more or less, and let's do it quickly now for category 3 as a reminder of how this goes. So I have an annihilation rate into dark matter stuff, which this annihilation rate is proportional to the number density of electrons. And I have a cross section, which is proportional to this coupling constant squared. And again, just 1 over t squared dimensionally for a light mediator. So for freeze in, the picture is a little bit different. If we look at this rate, it scales as temperature. So, sorry, this was 1 over t, or time. So it drops something like this for a while. Hubble actually is t squared, so it drops faster. So it actually is not in equilibrium early on. It starts to come into equilibrium. And then at some point, all these things are going to be too heavy. Either the dark matter is too heavy or the electrons are out of equilibrium, so there will be a huge suppression. It'll drop. So this is H and this is gamma. So in this case, we are producing dark matter slowly, and almost all of the production is whenever the cutoff is in this rate. So if we take the dark matter mass to be around an MeV, around an electron mass, this will cut off at around an MeV.
You said it starts to come into thermal equilibrium, but most of the things that we've been hearing about freeze in is that it never was in a bigger thermal equilibrium, like never gets that far.
So that's a good point. I think my plot is actually, let me change my plot so it's a little, sorry, my plot is misleading. This never gets into thermal equilibrium, so I should draw it like this. I should translate this all that way. Yeah, in this case, it never gets into thermal equilibrium. So
if since Friesen is a different, they were saying that the dark matter, that YDM equals EV over MX thing, is saying that the abundance at freeze out. Friesen being such a dramatically different mechanism, what is the equivalent to freeze out at that point? Is it just a direct translation, so that's the abundance at freeze in?
yeah, exactly. So in this case for freeze in, it's whatever, the condition is whatever time or whatever temperature the dark matter number density stopped changing. I should take that and set it equal to this. So in this case, we see that the dark matter number density basically stops changing when I get to this threshold set by mx or me, but let's just take the two mass scales to be the same. And so the number, to estimate the number of dark matter particles I produce, what I want is, I want to take this rate and multiply it by the Hubble time. So that's, Hubble is an expansion rate, so I want to multiply it by H inverse. So that tells me per electron how many dark matter particles I produce. It's going to be much less than 1 because by definition I'm not in equilibrium. So the number of dark matter particles is going to be like Ne gamma H inverse and Yx is going to be like just gamma H inverse because Ne and entropy both scale like T cubed.
Since we manifestly have more dark matter than non-dark matter, and you've said that we're assuming that the electron and dark matter particle masses are fairly equivalent, how can you have fewer dark matter particles than electrons and still have more dark matter total?
We can still have more energy density in the dark matter because it's non-relativistic. And so even though, remember we looked last time, if it was ever in thermal equilibrium, it would just have way too much. So what we want is a small density that, a small number density that, due to the fact that it's non-relativistic and stable, becomes a large energy density today. Okay, so I ran slightly out of room, so I'm going to finish this estimate down here. So if I plug in now the rate, this is my inverse Hubble factor. So this is Yx. This is equal to EV over mx. Like I said, I'm going to replace all these t's with just, well, it just becomes 1 over t or 1 over mx. So for freeze in, I get that the coupling, the product of the couplings has to go as an EV over m Planck, square root of that. And it's going to be of order 10 to the minus, well, this is 10 to the minus 14, but I dropped some order 1 factors, but it'll be in that ballpark. It'll be about, it's, in reality, it's more like 10 to the minus 12 or so. And I just write this. Okay, so the reason I've introduced this and gone over this again is because even though this coupling combination is very small, which would lead you to think that this is much less detectable than the other case, by the end of today, we'll show that, we'll look at this example again and see that the direct detection cross-sections turn out to be quite similar between case 1 and 3. And so this is actually a potentially detectable benchmark. Okay, so that kind of wraps up the summary from last time. Any questions or other comments from last time? Yes?
How do you make sure the mass matter will be cold if they're light?
So so the question is, how do I make sure they're cold? If the mass is greater than an electron mass, then it's still going to be cold by the time structural formation happens. So in this case, you can imagine it has like a similar temperature as the electrons as it's being produced, or a similar average kinetic energy, but then by the time we get to, at that point it starts to become non-relativistic and its kinetic energy drops even faster if it's decoupled from the standard model, so it'll be cold. Yeah.
Sorry, this is still bothering me. Since the electrons are also non-relativistic, how do you wind up with more energy in dark matter than you do in the electrons?
Just that the electrons annihilate away because, well, they efficiently annihilate away.
Okay, so
Yeah.
you don't keep having fewer dark matter particles than electrons. It's just saying this is for that rate in that early point.
Yeah.
Okay.
Yeah. Okay, so given, me write also the allowed kind of mass range for each of these benchmarks. This one, we've kind of discussed a lower boundary of around an MeV to GeV. Well, and higher, but I'm just focusing on sub-GeV. While these two are potentially as low as keV, or 10 keV, let's say, up to GeV.
So we've had a lot of different lower bounds on the thermal relic dark matter in the last several lectures. And I wonder why are they so different? So like we've had ranges saying that it can't be below 1 keV, can't be below 1 GeV, can't be below 10 MeV. Why the big range of these stated bounds?
So the two, so yeah, there are a bunch of different bounds, and obviously all of them have different assumptions. But one of them that's pretty generic is around a keV because of this, sorry, stop rolling this up and down, is around a keV because of, again, the fact that we see structure formation back up until temperatures of around a keV. It depends on the dark matter temperature, so that's why we always put squigglies and say it's around a keV. And the other has to do with BBN, so that's around an MeV, so those are the two that are important. Those are the two that are most important to remember.
Sorry.
Okay.
So
Yes.
Is the keV to GeV one, is that for the secluded or the freeze end? I can't tell.
In principle, both.
Okay.
Yeah. Okay, so one of the things I motivated last time was if I look at sub-GeV, I need new light mediators. It introduces, well, due to the light mediator, there could be some portal with a standard model, and there's all sorts of experimental ways to test that. So I'm going to start today with a slightly, take the most negative viewpoint in that I want to ask whether we actually need a detectable coupling to the standard model. If we look just at the secluded case, it's not obvious that we need a very large coupling to the standard model, and we want to ask then if that model is viable and what the potential tests are. So just a brief outline of today. I'll go over the cosmology of secluded, then cosmology of, I guess the scenario 1. These numbers don't map into each other. And discuss some things about all the constraints on portals. Okay, so let's start with asking, do we need a coupling to the standard model for the secluded case to work out? Any thoughts on this?
If we did not have coupling to the standard model, what we would be doing is producing a bunch of this unknown mediator thing that it would not couple to the rest of the standard model. So would that not mean essentially we just had two species of dark matter question mark?
Mm-hmm.
Like it would be, it's something else?
Right, so the comment is, let's say we don't, if we don't put this mediator to have any coupling with a standard model, and we don't see, it doesn't look like it can decay, and it's stable, then it would kind of just be dark matter. So if I allow this mediator to be quite massive, say above a keV, is that allowed? No, because? Sorry, so if I pick the mass to be above a keV of the mediator as well. So I make them both cold, but somewhat massive. And somewhat massive, yeah. Exactly, good. So the comment is that even in number 2, if we allow both of them to be kind of components of the dark matter, if I'm assuming that, I've assumed that this dark sector or this annihilation process is in equilibrium, so that dark sector is in thermal equilibrium. So if the mediator is very massive, then I still end up with way too much of this dark sector energy density.
Also, if they have masses, don't they at least have to couple to the Higgs?
It could be a dark Higgs or yeah, something else setting the mass. So we are going to want either the mass of this new mediator, which I'll just call MV, to be very small, much less than an EV, or this mediator could decay to some very light thing, some dark radiation, where the dark radiation, this thing has a mass much less than an EV. And that was because we saw last time, well, we saw also from writing this, relic energy density up above, for anything which is greater than an EV, we will have a big contribution to the energy density, and it would be like a component of hot dark matter.
If it can decay to dark radiation, then does that not violate the statement that we need the dark matter to be stable? Like, what's going to prevent it from doing that all at once in the early universe and leaving us with no dark matter today?
I'm just assuming that the mediator decays, so I still can have like a Z2 or something for the dark matter. Yeah. Okay, so now we've identified some scenarios where we dump this excess energy into new radiation. And there's some once I talk about new radiation, so either the vector is the new radiation or this, whatever this new R I wrote was, this dark radiation. And once I say that, I guess probably for a lot of you it comes to mind, we have to start thinking about N effective. Okay, so let's define N effective, which, well, let's define delta N effective, which is a measure during BBN or CMB of how much extra energy there is in a relativistic species. So the way it's defined is first, I'm going to just write the total energy density in relativistic species. So for photons, it's here. For neutrinos, I have my N effective, the one that's around a little bit above 3. Then I have 2 for spins, 7/8 for fermions. And then the neutrino temperature. Sorry, these powers are. Sorry about this. I don't know what to use now for new. I'll make a little mark for new.
Thank you.
We're not gonna have neutrinos for too long, so. And then we have our dark radiation. So again, the proliferation of G's, but these are the degrees of freedom. I'll just write this as some G effective I to account for the fact that they could be fermions, and whatever my dark sector temperature is.
You're mixing up pi square, right?
Yes. So NF delta N effective is defined relative to the total energy density in the neutrinos, right? I want to kind of write the dark sector part into the same form as the neutrinos. So then if I just write out these factors, this introduces this factor of 4/7. Okay, so the current constraints come from two different epochs. So we have the BBN epoch, which is going to be around an MeV, and that constrains delta N effective to be, I'm putting squiggles out for a reason I'll explain, about 0.5, and actually similar for both for C and B. So what happens if I increase delta N effective is that I change the expansion rate during nucleosynthesis. Sorry, just looking at BBN. If I change delta N effective during BBN, I increase the expansion rate. This changes the number of the neutron to proton ratio because that's set by the rate of the that's set by the transition between the collisions that keep proton neutrons changing back and forth in equilibrium. I'm losing the word. And I want to compare that with the Hubble expansion. So it changes what the fraction of neutrons is left over.
If this dark stuff doesn't interact at all with standard model, why does its just sheer existence change the ratio of protons to neutrons?
Right, it just changes the Hubble expansion during BBN,
okay.
and that changes the proton. Yeah. And so what you have during BBN is if you increase the number of neutrons, basically that means more heavy things can be built up, so it increases deuterium, increases helium. And that's where the bound comes from. And there's some prospects for doing much better with CMB stage 4. This is probably on 5 to 10 year time scale, but impressively they claim delta N effective can be, well, let me write it this way. Their 1 sigma projection for delta N effective, or their error bar, is about 0.03. So it's a full order of magnitude. Good point. I think these are 2 sigma actually. These are, yeah. And the reason I put squiggles is that, well, for instance, for CMB bounds, you always have to be careful because the more ingredients you put in your default model, the more this can relax. If you allow, for instance, sterile neutrinos, or if you allow for non-standard neutrino interactions, people have looked at that, and that can change this bound a bit. So in the most kind of pessimistic scenario, we've imagined that this secluded sector doesn't really talk to the standard model thermal bath at all. But it did have to be, we did need to populate this sector at some point such that it was in thermal equilibrium. So let's suppose that there was some higher dimension operator that led to dark matter being in equilibrium with the standard model particles at very early times, or some time well above BBN, and that this process decoupled, and then we just have a separate dark sector thermal bath that does freeze out and leaves behind some radiation. So let's see if we assume that the thing I want to do is say if it was an equilibrium with the standard model at a given temperature, what would be the delta N effective that we see? Okay, so at some initial time, I'm going to call it decoupling, the two sectors had the same temperature. After decoupling, the standard model particles, we remember, well, what I plotted last time was the number of degrees of freedom in the standard model. And as those degrees of freedom go out of equilibrium, we saw that the temperature goes up a little bit each time. So that raises the temperature of the standard model sector relative to the decoupling sector, or sorry, to the dark sector. And the more time there is between decoupling and BBN, then the more we can kind of decrease this delta N effective to satisfy the bounds. Okay, so let's compute that. So at this time, the dark sector part had, I'm going to assume very minimally just 2 degrees of freedom, meaning both the dark matter and the mediator. Obviously, if that assumes also that they're scalars, just to be as minimal as possible. Okay, so now I want to get this dark sector energy density at, say, BBN.
Since I think we've established that we're saying at decoupling that the temperature of the dark stuff is equal to the temperature of gamma, but not necessarily afterward. Is that rho dark? Is that T in there? Is that the bath or is that the dark matter?
This is at decoupling, so I can just put gamma.
Okay.
Yeah, and afterwards they evolve separately.
Okay. So that rho dark is actually, are you saying that that's a constant?
No, this is just
Oh,
at
we're
this
still
time.
evaluating
Yeah,
at decoupling.
this is like
Okay, sorry.
at this time. Yeah. So if, write it this way. If this sector had the same, evolved the same way as the photons, we know what happens. But since it doesn't, we have to increase this. Sorry, let me write it this way. So let's just track until, let's first just track until just before neutrino decoupling. So I'm just going to write this as T nu because that's what we want in the end. I'll get there in 1 second about the 2 degrees of freedom. So ignoring the 2 degrees of freedom for 1 moment, this would be the energy density if it was still in equilibrium, and because it's not, I need to include the ratio of the G stars, the degrees of freedom, at the 2 times. Okay, so remember that A cubed S was the conserved quantity, and so if we and S was G star to the T cubed. So this tells us something about the relative temperatures at different times, and so the relative temperature scale as G to the 1/3, and since we have a T to the 4th here, we have a 4/3 power of the 2 G stars. And the other thing is, if I have this dark sector, if in the dark sector this annihilation process XX to gamma gamma, not gamma gamma, VV, happens before this MEV temperature, then a similar process happens in the standard model, in the dark sector, which is that I have 2 degrees of freedom. One of them annihilates, and so that raises the temperature of the remaining radiation a little bit by a factor of 2 to the 1/3. So I'm going to put a 2 to the 4/3 here. This is only if it's more massive than an MEV or so. Okay, so these factors account for the fact that the dark sector temperature would be lower if, ignoring decoupling, would be lower just due to the fact that the standard model bath has a changing temperature, and this one accounts for the freeze out of the dark sector. Yes?
So that temperature should be photon temperature. Or either you ignore this L1 factors relation between neutrino temperature and photon temperature.
Yeah, so exactly. That's why I put G star MEV here. So I do this up until MEV temperatures before neutrino decoupling.
Okay, at that moment that's...
Yes, and then you can do it after, and then you have to account for it just adds an extra step of complication because you have to account for the fact that G star from an MEV until after E plus E minus. So someone asked yesterday about using entropy of neutrinos, or of photons versus photons plus neutrinos, and I kind of just glossed over it because I don't want to go into detail, but you do, similar to what I did here, you just have to be a little bit careful about before neutrino decoupling, it's easier to just use everything, including neutrinos, because it's an equilibrium. After the neutrinos decouple from the standard model, then you kind of switch to everything else that's in equilibrium. So you just have to be a little careful there. But so that's just a technical detail. So this tells us, yes? Yes, yeah, exactly. I want to compare with the temperature neutrinos. So I can just look at how the relative temperatures are, how the relative energy densities are just before the neutrinos decouple. After that, the 2 sectors will kind of redshift in the same way. Yeah, so by MEV, I just, before neutrino decoupling, I should be more specific, yeah. Okay, so now let me sketch this, what this looks like. So now I have the dark sector N effect, or I have the energy density, and I can turn this into a delta N effective. Probably going to get all these bumps wrong. Sorry, this is about 10 MeV. So this is the delta N effective as a function of when the dark sector decoupled. So there's a big jump here, again, because of the QCD phase transition, where the standard model sector suddenly has a much higher temperature or gets a lot hotter compared to the dark sector. I didn't label this axis very clearly, but I'll do it by showing what's excluded. So my BBN/CMB bound sits at around here. Currently, it's still allowed to allow the two sectors to be in equilibrium just somewhere above the QCD phase transition. Then you can sufficiently decrease the delta N effective. But interestingly, the CMB stage 4, I believe I'm drawing the 2 sigma, but I can show you the plot afterwards if necessary. So the CMB stage 4 projections will be able to reach pretty high in the decoupling history of a potential secluded sector. So up to around 10 or 100 GeV, it will be able to tell if there's something in equilibrium with the standard model, and of course assuming that I didn't introduce a ton of new standard model degrees of freedom or other degrees of freedom below 100 GeV.
So that CMB stage 4 thing, where they're saying they don't expect to bring this, does that mean they expect to actually find no delta N effective, and so they expect to be able to say it's less than 0.03, or that they expect to constrain the value to within plus or minus 0.03? How sure are they that the true value, as it were, is 0?
Oh no, this is, yeah, exactly. This is just an error bar, their expected error bar, and this is their 2 sigma error bar roughly. If I take their 2 sigma error bar, it would be able to go around here. Okay, so this tells us that these secluded sectors are not entirely hidden. We do have ways through delta N effective measurements to go pretty far back in our cosmic history and test whether they were ever present. Of course, you can always keep pushing higher and higher and do it at reheating with very high reheating temperature, but it's still impressive that these delta N effective measurements will go up to almost 100 GeV. And also remember, I just picked the most conservative case of 2 scalar degrees of freedom. It's very conservative because in most models you're going to have fermions with a bunch of spins, vectors, and so on. And that will definitely raise this delta N effective. Okay. So there's a way from cosmology to test secluded sectors. Another important set of tests relates to whether there are self-interactions in galaxies. Ooh. And that's because I've introduced, well, self-interactions slash, I guess there's 2 things. So we identified 2 possible scenarios. This mediator is very light, or the mediator decays to dark radiation. So if the mediator is light, it can mediate these self-interactions. And as I'll show shortly, the self-interaction constraints actually exclude a lot of the light mediator scenario and force you into the part of the parameter space where, or force you into models where the mediator decays to light radiation.
What happens if the mediator is heavy and is not decaying?
That's our overclosing the universe constraint if the mediator is heavy. Okay, so just to summarize, if MV is less than an EV, we care about self-interactions. If it decays to dark radiation, you can have other interesting effects in the CMB, things like dark acoustic oscillations and so on, but I'm not going to talk about that because you have potential scattering between the dark sector and this radiation. Okay, and so for this, there's a recent review that you can look at. Yes? This too, I assumed that the dark matter annihilated into the VV, and this raised the VV temperature a little bit. So it's sort of like the E plus E minus in photons case. There's a little increase in temperature, and that's what I put here. Yeah, you're right. So you're saying if dark matter is very light, then this still is 2 at the time of MEV. The heavy, if the heavy degrees of freedom in the dark sector contribute by increasing the temperature. They don't contribute directly as a degree of freedom, if that's what you're asking. Is that? Yes? Oh, the technique? I don't know the details of where they got this estimate, but they'll do small scale, they'll do like high L, and they'll do polarization, and I don't know exactly which one it comes from. Yeah. Okay, so very quickly, let's do self-interactions. So this mediator coupling allows things like this. And the current constraint is given in terms of the cross-section per unit mass. And there's a lot of debate about exactly what number and what system you look at, but so I'll just put a range of 1 to 10 centimeters squared per gram. And to translate this into well, just to give you an idea of where this comes from, let's estimate our rate for self-scattering in a galaxy. So it's given by my number density times times the cross section times some typical velocity, which I'll put as could be around 10 to the minus 3. And we know that the energy density locally in the Milky Way is about 0.4 GeV per centimeter cubed. We replace this with the constraint. I'll just put 1 and 10 to the minus 3. A gram in GeV is about a mole, so we get 10 to the 23 here, get about 10 to the minus 26. Sorry, I need my centimeter. I need to restore my units here. So my velocity is 10 to the minus 3 in units of C, so I have another 10 to the 10 centimeters per second. Okay, so I get 10 to the minus 26 from here, and another 10 to the 10 here, so I get 10 to the minus 16 over second. And if I compare with galactic time scales, so that means scales on which galactic dynamics is mostly relevant, that is about 10 to the 16 seconds. Translated, it's about 100 million years or a billion years or so. So it's basically just saying, these constraints are basically just saying, I should not have more than one interaction over the age of this galaxy, roughly. And for a light mediator, this is a pretty strong constraint. I can write this cross-section, say the mass of this mediator is similar to the mass of the dark matter. So in the non-relativistic limit, it's going to be something like this. And so the fact that I have a light mediator means this can be pretty large, especially if you compare, for instance, these numbers kind of translate into what you expect for QCD if this is around a GeV. And so all of these scales are similarly below a GeV. Then even for order 1 couplings, this can approach this limit, this cross section. And now we can ask if this coupling is the coupling I need to set the relic abundance through that annihilation process, what does that mean for the mediator mass? Right, so I need at least some sort of a minimum coupling here to get enough annihilation. So if I keep reducing the mediator mass, then I'm going to start to saturate this bound. So for a given dark matter mass, I can put a lower bound on the mediator mass. Try to get the scale right. And that bound looks something like this. Sorry, it's supposed to be a straight line. Well, it looks roughly something like this. So everything below this line is excluded by self-interaction, assuming that I get the relic abundance through this annihilation to the mediator with the same coupling. And if you've been, some of you might have been following, there's an interesting region around here where it's claimed that you can actually you don't use it as a bound, but you can actually explain some of the questions in small-scale structure. If you want to explain some of the profiles of dwarf galaxies and so on, then there's some parameter space up here, which they claim satisfies the constraints from things like clusters, but fits the observed profiles in other dwarf galaxies. Okay, so there are ways to test this secluded scenario. They mainly involve delta N effective, self-interactions, and so on. It's not necessarily guaranteed that you can still have a scenario work and not be testable if you really push everything up to high scales. But this shows the ingredients you need and shows that you do have to work hard to evade the bounds. Okay, are there any questions about this? Because now we're going to turn to the not secluded scenario and start talking about direct standard model, direct annihilation to standard model, and the ways we can look for that coupling. Okay. So let's just do E plus E minus through this mediator. It was mentioned that there's a bound from BBN at around a few MeV. So I just want to discuss this a little bit because sometimes this is called a delta N effective bound, but it's not exactly the same as the delta N effective bound I put here. If you increase the radiation density, you increase both of those things. But if you leave something in equilibrium with E plus E minus, that has a different effect. It leads to essentially more efficient conversion of deuterium into helium, so it does this. So it's a slightly different constraint. And the reason it does that is when there's something additionally in equilibrium, it changes kind of the baryon to photon ratio for a little bit, and that has a different effect than changing the expansion rate. So we have this. And it's model dependent exactly what the bound is. Again, you have to count the degrees of freedom at BBN as well. Okay, so our direct coupling scenario is good down to about a few MeV. There's another let me put the reference that goes through some of this. forgot the last author. So there's another very important bound for sub-GeV dark matter if I have a direct coupling. Does anyone know what it is? If I can annihilate D plus E minus. So Dan has not gotten there yet, but a huge constraint comes from CMB again. If you have the thermal relic cross-section, remember that this process is out of equilibrium, and it happens very rarely after freeze out, but it does happen. So it's happening at a very slow rate. And what it does is it injects additional energy at the time of recombination. So if you dump a bunch of energy in, what happens is it can ionize the neutral hydrogen, and it changes your surface of last scattering because you have more ionized particles. And so that constraint looks like this is now the annihilation cross-section at CMB, which can be different from the one at freeze-out. Whatever this. So I have my thermal relic cross-section. And for the mass, it's about 100 GeV. So this is an incredibly strong constraint if you have additional annihilation at the time of CMB. So F is an efficiency. You can ask Tracy all about F. She's done all the calculations on F. Is an efficiency for the annihilation into visible things. So if you annihilate mostly into neutrinos, this F becomes almost zero because neutrinos don't ionize. And if you annihilate into photons, it's almost 1. So this says if you have the thermal relic and your F is order 1, then below 100 GeV is extremely constrained. But there's a way out, and the way out is just that this annihilation cross-section is the one during CMB, and that does not need to be the one during freeze-out. You can do things like P-wave, asymmetric, inelastic, or co-annihilation, so on. Okay, but these are the kind of the zeroth order things you need to consider when doing these sub-GeV directly annihilating to standard model stuff.
You said that F first is annihilating to photons is close to 1, and if it's annihilating to neutrinos is close to 0. It's annihilating to electrons or some other order. What kind of order is that F?
So F, if you're annihilating to electrons, is also close to 1. If it's quarks, it's going to be about, I think, 1/3 or so. Okay. Yeah. Again, you should ask Tracy for all the details. So none of these bounds that I've discussed apply for freeze-in, because freeze-in, it was never in thermal equilibrium. So I don't have to worry about delta N effective. And I'm never going, in freeze-in, or the rate for annihilating into E plus E minus is incredibly small because I was never in equilibrium. So freeze-in satisfies all of these. That's why I'm allowing down to KeV. Right, so yeah, these different cases, P-wave means that the annihilation cross-section has the leading order scales as velocity, and the velocity at the time of the CMB will be very, very small. Asymmetric, you annihilate away, so you get a suppression due to the fact that there's nothing to annihilate with the CMB. And inelastic or co-annihilation, those things are also similar, or they also use the fact that the kinetic energy is very low, so if your process depends on having kinetic energy, it goes away. Yes?
In the Volta paper and delta N effective is the length different, right? Like it's dependent
I think it's defined the same in this paper as what I've written, but yeah, we can go over that. It should be, unless I have a typo or something.
I had it up a second ago, and it was definitely defined as the ratio of neutrino to gamma.
Okay, I mean, they might have written it differently, but yeah, let's go over that after.
Sure.
Okay, so that's these are the broad considerations for the cosmology of the direct coupling scenario. And so far I've been very agnostic or just general about what I mean by direct coupling. So the next part, we want to start being a little bit more specific and talk about what possible portals there are. So okay. One of the most popular, probably everyone knows, is a dark photon portal, kinetic mixing. Okay, at this point, I wrote down a bunch of portals in my notes. It's probably not complete, so feel free to shout out your favorite one. Any others? I cannot remember them all. Higgs? So which Higgs portal do you mean? Do you mean like a scalar which mixes with the Higgs? Yeah, good. Higgs. Yeah, so this would be my mediator, and it can generate, I can get a mixing to the Higgs this way. Neutrino. Neutrino, you still have to add something, so I'll put it down, but so far we're working with kind of these S-channel mediators and putting in a neutrino here. I still have to add in some other things, but yeah.
So can you translate that? What's L and H?
Oh, I just wrote down like this is left-handed lepton doublet Higgs, and then some, yeah. Nobody likes other portals. Inflaton, what? Oh, I don't know what that one is. I'll write it down. What is it? Okay. Okay, it couples to the inflaton. Most of these portals are portals to the standard model, but I guess you can say the inflaton is in the standard model. But that's fine, yeah. Let's talk about, yeah. Other portals. Which axion portal do you like? You're agnostic. Okay, I'll put them all down. I'll put this one. I'll put down this one. What? Oh. Sorry. I can do the same with a scalar also here. Just put a new, if I have some new heavy colored things that couple to the scalar, I can generate something like this, with or without the squiggly, sorry, without the squiggly. B minus L, maybe. There are other bizarre combinations of some less bizarre, some more bizarre combinations of lepton and baryon number that you can pick that are anomaly free in the standard model that you could try using as a portal. Just be careful, there are extremely strong constraints if you pick something with anomalies or if you pick something that you cannot UV complete respecting standard model gauge invariance. So there are extremely strong constraints on U1 baryon, for instance. And also axial couplings, they're extremely strong constraints. By axial couplings, I mean just kind of writing down something like writing down a new vector with some axial coupling to standard model fermions directly like this is, once you try to complete it respecting gauge invariance, it can become problematic. Let's put an X here. Don't do it. Okay, so I just want to summarize for two kind of classes of portals what the constraints are. And I want to pick two because they have very different behavior in the very low mass limit. So a good exercise that I have to do every year or every month or very often is always reminding myself how these field redefinitions go. So I'm going to start with a dark photon, and I'll write it as a kinetic mixing with hypercharge because that respects my standard model. Sorry, I don't want to, what did I call it? It's usually called B. So for the dark photon portal, this is hypercharge. And apologize for changing the notation. I'll change it. This is the kinetic mixing, and I just put in here, I'll put this back to kappa. Sorry about that. I put the cosine of I put in the weak angle just to make sure that when I go to the photon, this weak angle disappears. So it's helpful to always to go over this every once in a while, but I'll just write down what happens when I diagonalize the gauge boson kinetic terms and look at what matter couplings I have. You want me to use the board behind this one?
Yeah. It's really hard to read.
Oh, because of the lack of water. Yeah. Okay, I'll write on here. So this becomes a coupling of electromagnetism with the dark electromagnetic current with the dark photon and a coupling of the dark current, meaning whatever's charged under the dark photon with the Z, plus corrections of order the dark photon mass over the Z mass. So we often see this one because we know that the photon has to remain, is the massless state, has to remain massless. So we generate a coupling of the current that couples to photons with the dark photon. This one is kind of the opposite case. The Z is much heavier than the dark photon. So instead I generate a coupling of the dark current with a Z. Okay, and here's the dark photon. Oh yeah, probably, yeah. And I keep changing between the two. Yeah. So above about an MeV, that's where most of our collider or accelerator, let's say, things become relevant. We can look for things like directly decaying into E plus E minus. I'm going to go all the way down to 10 to the minus 16 eV. It means other terms that are proportional to this. There's a coupling of the like yeah. There's a coupling of there's this like J mu Z V mu kind of thing in there, yeah.
It's interesting that there's no mass terms in anything before then. Normally, when you order something squared,
Yeah.
there's a linear term.
So because it's in the kinetic terms, the mixing.
Oh, okay.
Yeah. So there's an important effect for the constraints on dark photons. This is going to be from 10 to the minus 15 to 10 to the minus 3. And if you don't like my rendering, I think this review has a lot of the constraints. It's slightly older, so it doesn't have all of them, but it does go through a lot of them. There are stellar constraints, like so you can produce these things in a supernova, and that constraint goes up to about almost 100 MeV, set by the temperature of the supernova. I'll kind of write it like this. And you can also produce these dark photons in other stars, and those are not as hot, so they kind of look like this. These wiggles are just my shaky hand. So this is stellar. So they kind of go. And there's an important effect for dark photons, which is that all of these kind of stellar constraints start to turn off for low masses. So they're in medium mixing effects that are very important, and they suppress the production of these dark photons. And all of these turn off. And so there's actually quite a bit of room here for fairly large couplings. There's some sort of CMB bound. This is, again, an in-medium mixing of the, it's an oscillation between the photon and the dark photon, which depends on the in-medium mass of the photon. And there's a similar thing around here. They looked at various targets and looked for this kind of mixing effect. So when we have dark photons, when we look at models of dark photons, we can have very light mediators, 10 to the minus 11 eV or something, with fairly large couplings. If we're looking at something like the Higgs portal, or almost, or say B minus L, or anything like that, there's a very important difference, which is that these stellar constraints don't turn off; they kind of stay flat. And there's very strong fifth force constraints that go like that. So if you have, say, B minus L, then the charge of an atom is, well, there's no electric charge of an atom, but you can have a very large B minus L charge, and so there's extremely strong fifth force constraints. Okay, so this is if, say, a scalar coupling to electrons or something like that. So that's the big difference in terms of model building.
So which side of that fifth force constraint is the allowed or disallowed?
This is all excluded, basically.
Okay.
And I have a paper with some plots showing how exactly this works for the scalar case. So in terms of model building, if you want to look at the, generally model building, you're in this region, in the high mass region, for any mediator that's not a dark photon. Okay, but I want to show now that, or I want to write down now 2 benchmarks that, that have the correct relic abundance through the dark photon mediator. I'll show where they live in this parameter space for the dark photon, and then we'll wrap up there. So I've been fairly general so far, but I just want to present two benchmarks. Sticking to this dark photon mediator. So the first is this direct annihilation into E plus E minus through a dark photon. Sorry for the change in notation, I'll stick to V. That is slightly heavier than the dark matter. So let's say the dark matter mass is about 10 MeV. The dark photon mass is about 30 MeV. And I want to satisfy the self-interaction constraints. And I can do that even with a... Yeah, the dark photon can be more massive. I just go through this annihilation. I can satisfy the self-interaction constraints even with a fairly large GX coupling. And the coupling here is given by kappa times the electric charge, which is coming from this one. And that kinetic mixing can be about 10 to the minus 4. So let me mark this with the yellow, green, purple dot. And that benchmark will be somewhere in here, right in the middle of these accelerator tests of dark photons or dark matter coupling to dark photons. There's a direct detection, there's a definition I want to make of a direct detection cross-section for scattering with electrons. And I'll motivate this definition a little bit more when we get to direct detection. So this definition comes from, so this bottom part of the definition comes from the fact that I'll have some sort of propagator that looks like q squared plus mv squared, or minus mv squared. And then I can replace, there's a typical momentum transfer that I'll be able to replace this with. But so for the moment, this is the definition of the direct detection cross-section. And I claim if you plug in these numbers, this will be about 10 to the minus 37 centimeters squared. The other benchmark in the last minute will be the freeze-in benchmark. Mx is still around an MeV. The dark photon mass now is very, very light. What did I pick? 10 to the minus 12 eV. To satisfy the self-interaction constraints with such an extremely light mediator, I need to now turn down the dark matter coupling with the mediator. So it's about 3 times 10 to the minus 6. I just need to pick this kinetic mixing to satisfy the bounds I sketched over there. So I can pick about 10 to the minus 6. So that benchmark is going to be somewhere around here, just below the constraints. Okay, and the point I want to make is that we see in this freeze-in benchmark, we've picked these extremely small couplings in order to satisfy the first thing we derived to get the relic abundance. And it satisfies the existing constraints. The interesting thing is if you plug in the numbers for this direct detection cross-section, it is similar. It is also on the same order as the one I showed here for very large couplings. And that's coming from the fact that when I have a very light mediator, this part goes away, and there's just the momentum transfer part. When it's heavy, it's suppressed by the mass of the mediator. Okay, so these are sensitive to accelerator This one will be sensitive to, well, accelerated and direct detection, and this one will be mainly direct detection. So I'm out of time, so I do have some notes I uploaded estimating how to do estimates for the accelerator bounds. But now that I presented some benchmarks with some pretty large direct detection cross-sections, what I want to do in the remaining 2 lectures is just then start to focus on calculating direct detection rates and how we can get to these kind of cross-sections with sub-GeV dark matter electron scattering, or, as I'll discuss, phonon scattering. So that's it for today. Any questions?
So you said it was the dark photon. And my understanding is the dark photon is basically quantum dark radiation. But if you've got a 30 MeV particle, which is more massive, I don't see why that's radiation. Or in what sense that it is photonic? Like,
In this scenario, I'm not taking the dark photon to be like dark radiation.
okay.
That was only for the very first secluded scenario.
Okay.
Yeah, when I don't have this process. Yeah. Okay. Yeah, feel free to ask more later. Thanks.